So yeah, guys, I think so. We are live now. Yeah, let us wait for a moment. And yeah, we are live. So yesterday we did the marathon for the part one, where we see the UT paper, and now we are doing here this part, which is question paper remaining half. Yesterday we have did till question number three. Am I correct, guys? Now we are moving forward and doing the next part. So till the time, let's see what we have done yesterday. This binary to octal part. Then we have did the symbol of XOR gate, then the De Morgan's theorem, then converting this expression to the standard SOP, sum of product form. Then we have wrote a symbol and write the truth table of D and T flip flop. Okay. After that, we have moved towards the clock pulse required. Sorry, number of flip flop required to count 16 clock pulse. The formula, then type of PAC, second complement subtraction, then expression of logic gate, we have to implement the Boolean expression. After that, we have done the scheme map question. Then the demultiplexer, we have used the function. Okay. After that, we have made NAND gate using OR, NOT, and NAND. Okay, where we have shown the truth table, then the K map. Okay, and yeah, after this, we have to write the JK flip flop working in truth table diagram everything. Okay, given the question. So which we have wrote. After that, we have to describe the working of 4-bit Cisco serial in and serial out shift register with diagram and waveform. So the input is given to us 01101. After that, we have now, like the next question, which is question number 4. Yesterday we have did this part, CISO shift in, serial in and serial out. Today we'll start from this question number 4 part. Okay, so what's the thing we have to draw a full adder using truth table, key map, everything. So first we have wrote what is the full adder. Okay, full adder is basically a combinational logic circuit that performs addition between 3 bits and the input, the two input, which is A and B, and the carry C are from previous bit. Means we are giving 3 inputs and getting only 2 outputs. This is the main part, okay, which is happening in a full adder. After this, in full adder, these are some of our truth table, okay? Now, if we like observe this properly, this is the binary, okay? Now, binary for one, binary for 0, 1, 2, like that. So let me just write here 0, 1, 2, 3, 4, 5, 6, and 7. This is the binary. Now, what binary exactly is like? We have wrote this last time 2 raised to 0, 2 raised to 1, and 2 raised to 2. Means what it is exactly? It is like 1, 2, and 4. So, if all of those are 0, it is means 0. If this is 1, so these two are 0. Means the binary decimal. I think so everyone knows binary decimal. So here it will be 1. If it is 2, then the square will be there. As we can see here for 2. For 3, both of these will be there. Now these are some of our inputs and the output we are getting, which is sum and carry. Now let us understand this part. There is all zeros, so we gave 0. Okay, no carry, no sum. Now there is 1. If we add all those numbers of this line, okay, like 0, 0, 1. So what are we gonna get? 1. And nothing will be carry, so the carry part will be 0, which will again come down. So carry 0, sum 1. After that, same here as well, even same here as well, but we are getting two numbers. So like 0, 1, 1. If we add 2, 1, 1, we get 0, but the 1 is again carry. So this is the carry part, okay? So here we have wrote 1 in carry and 0 in the sum. Same. Now here we can see there are 3 times 1, 1. So what are we going to do here? 1, 1, 1. We are going to add 3 of them. So 1 plus 1 is always 10, okay? As we know, so like 1 and a 0 is like carryover kind of that, all those part. And then this 10 plus 1, which gives us 11. So 1 here and 1 carry over. Okay? So those are our sum and carry. I think so. The truth table is clear to everyone what is happening exactly here. And this diagram. After that, we'll move to the next part, which is the K-map simplification. Now, example, if the zero is being present here, what are we going to write? Once the zero part is present, we'll write 1. If not, we'll write 0. So what is exactly present? This 1, 1, 1, and 1. Now, how it is exactly working? This 0 and this 2 0. This 0 and this 0 1. Then 0 and 1 1. So 0 1 1. Then again 1 1 1. So 1 1 1. And then this 1 0 1. So 1 0 1 and 1 1 0. Those numbers are present in the carry part only. Okay, so this is the carry part, and here only this numbers have been present from out of 7. So 4 are present. Same here, 4 are present, which we can see properly. So this is how things have been working, but this is for some part. After doing this, we are getting some equations, correct? Those equations are important in order to understand the part. Now, after that, we'll draw the logic diagram where those equations are being represented in logical diagram. Okay, so now what are we doing exactly here? In this diagram, if we see properly, we are giving three inputs as we mentioned and getting two outputs, which is sum and carry out. Where in inputs we can see the same input line has been given to all of those four logic gates. Correct? Here and this one. This is for sum, the individual part, correct? Which we are getting output, the sum part. In this equation, which we have shown here, then we get the carry out part, which is by combining all of those three logic gates. I think so. This is clear to everyone. Now we'll move to the next question. If anyone is having any doubt, just comment below, okay? Now, describe the working of a ring counter using D flip-flop with diagram and waveforms. Now here the input is not being given for waveforms, so we'll consider from ourselves, okay? Like something like this. Now what is the diagram? Here CLR, CLK, and this reset, okay, reset. Okay, here it is like the reset. Okay, this is CLK. So now, what is A here? A is the what do we say? The alphabet or the kind of thing given to this part. Okay. Then this is the B and C. After that, things have been like QA, QB, QC. The flow where the current is like you can see going especially. Then we have gave the names like D and Q everywhere. After that, what is exactly happening? The clutch. Uh, As we know, this is what the edge triggered, which we have studied in a D flip flop. Here, let me just show you that question once. The D flip flop. Uh, okay. JK flip flop will be not an issue. Okay. Okay. This is the D flip flop, not an issue. So this is how things have been working in D flip flop. Okay. Now after that, we'll write the waveform part. Here above, we have studied about other flip flop, and this is the D flip flop. Okay. In waveform, as we can see, this is the CLOCK clock. If we see properly, CLOCK clock. Then there, this is shift. So like SHIFT shift. Okay. Then this is QA, I think so, yeah. And this is QB, which is again 1, 0. And this is QC, which is again 0. Then we are having QD, which is 0. What it is exactly saying, if your bar is like up, so it will be 1. Okay. And if it is down, so it will be 0. This is how things have been shown here. Now, what are we doing here? We have wrote some numbers here like T0, T1, matlab time, kind of. Okay, so like we are writing here from till T8, okay, till T8, doing all these things. After that, we can see this is the above. So this is for 1. Now we have shown the shift register line from here, okay? After that, we have shown the QA. What is QA line here? As we can see, this QA. So we have shown that part here properly. After this, we have lived dismiss space and started here. See, living dismiss space again and again. Okay, nothing else. What is this exactly? This waveform. Now here we can see we are getting a basic working what is happening here. The ring connector, sorry, the ring counter is cascaded connection of flip-flop. Means it's the main connection of the flip-flop where the ring counter has been seen. Like in which the output of the last flip-flop is connected to input to first flip-flop. Means the output which we have got from the last person, means the last flip-flop has been connected to this exactly the first flip-flop, the input. Now in ring counter, if you see the output of any stage is one, means if your any stage is one, then okay, like then its remainder is zero. If it is one, then the remainder will be what, zero, as we can see here. Okay, the ring counter transfers the same output throughout the circuit. Nothing changed, same circuit, okay? That means if the output of the flip-flop is 1, then this is transferred to next stage. If the flip-flop's output is 1, then transfers to next stage. Example, the second flip-flop, which we can see for now. Okay, after that, now moving to the next part, where by transferring the output to the next stage, the output of the first flip-flop becomes 0. Okay, as we take it to the second flip-flop, the output becomes directly 0. Okay, now at the stage continues for all stage of a ring counter. If we use a flip-flop in a ring counter, the one is circulated for every clock. Okay, so one will be circulated for each and every clock scene. I think so that is clear. Now we'll move to the next part, means the next question, which is we just have to draw a block diagram of a programmable logic array. Okay, logic array programmable, where we can see these are the inputs. Okay, let me just write your inputs. Okay, don't worry. The PDF of this will be there in the comment. And then this is the output part. Okay. Here we can see this is the input buffer. This is the AND. This is the OR. Okay, same for this as well. And this is the outputs. Okay, outputs part. Now, what are we looking here? These are some things working here properly. Now, this is the inputs, which is T0, T1, T2, and yeah, T3. I mean, Tn plus 1 exactly. Okay, then here it's like L. So I think so it's LG. Like that. Things have been, sorry, LG not L0, L1 or T1. Then L2, then 3. And yeah, things are happening. Now here it will be L and minus 1 and same upon L and minus 1. Like that. After that, this is P. So P0, P1, and here it will be P n minus 1. Again, this is the S0, the S1 part, then it will be Sn plus, sorry, n minus 1. And this is the basic flop apps output buffer, where the outputs are given in the form of F0, F1. Yeah, so let us write this part. Outputs are F0, F1, F2, and Fn minus 1. Those are some of our outputs. Okay. Now, what is the difference between volatile and non-volatile? So yeah, what is volatile? Volatile memory. Memory required for electrical power to keep information stored in a volatile memory. And what is non-volatile memory? That keeps storing, sorry, that will keep storing its information without the need of electricity, without the need of electricity power. But volatile needs electricity and non-volatile doesn't need. In name only we can see none, means non. It is not required. Okay. Then volatile memory is for all classification of RAMs. Okay. But non-volatile is only for ROM, EPROM magnetic memories. Okay, now to the next question means or the same question, next point. Effect of power means that the stored information is retained only as long as power is on. Means if the power is on, it will be restored, but if not, yeah, then there must be issue. Like stored information retained power is on. And here if no power, no effect of power on stored data. Like it is not required exactly. As we can see, there is no in the name itself. Yeah, and oh, without. Okay. Then applications for temporary storage for permanent storage of data. Yeah. Now we'll move to the next part, which is EPROM and EEPROM. So EPROM and EEPROM. Okay. So now what we can see here, first, EPROM, what it exactly stands for, erasable programmable read-only memory. And EEPROM means electrically erasable programmable read-only memory. Okay, here it is 1 marks for each of 2 points. Yeah. So what is the basics? Ultraviolet light is used to erase the content. Okay, in EPROM. But in EEPROM, here we can see directly the EPROM contents are erased using electrical signals. Means the signals are necessary here in order to cancel this part. After that, the EPROM has transparent quartz crystals window at the top. So it has this, but EEPROM are totally encased in an opaque plastic case. Means it has crystals, specially. Okay, let me just highlight this. It has crystals and it has plastic special. Okay. After that, EPROM is modern version of PROM, correct? But EEPROM is the modern version of EPROM. I think so. This is clear to everyone. After that, let us come to the question number this part. Okay, so what are we doing here? Describe the working principle of successive approximate ADC. Okay, so now other relevant diagrams and explanation also can be considered. So this is how things have been shown here. First, we have shown the analog voltage, then how the offset voltage has been calculated half upon LSB. Yeah, after that we are showing RVA, which is again analog voltage and all. Then DAC converter. So what is happening? We are taking the analog voltage part in the plus and even the DAC. Okay, sorry, DA converter, not DAC, which is again here uh, giving the output in the form of VO. Okay, sorry, V0 with the help of comparator. Okay, now this comparator is further giving the output to the programmer. Even from the clock as well, the output has been given to programmer. When programmer processes this, the input is again given from TA converter and the programmer. This is again further showing LSB as an output and MSB as an output, which is in digital analog as much as I can. Okay, guys, here it is written. Now, on top of that, let us write this here. It's DIGITA, digital output. Okay, after that, things are shown how it is working. Now only explained, and this is there only in the format of this. As we can see here, let us read this. The successive approximate ADC shown in figure this. So this is a figure exactly shown above. It is having an analog voltage which is VA, which is again known constantly compared with VI. Okay, it is compared with VI, which is compared using a comparator, nothing else. After comparing, the output produced is V0, which is applied using electronic programmers. Okay, where we are showing that our VA is equals to VI and VO is equals to 0. Okay, I think so. Then after that, no conversation is required. The programmers display the value of VI in the form of digital output, okay, especially. But if VAVI, then the OP is changed by the programmer, means the output. If those cases happened, okay. After that, again, if VA is greater than VI, then the value of VI is increased by 50% from earlier value. Okay. But if it happens in different, so here the things changes. So it is decreased by 50 in this case. Okay. The new value is converted into the analog form. Okay. By DA converter as so as to compare it with a VA again. The it produces is repeated till we get VA is equals to VI. As the value of VI is changed successively, the method is called as successive approximate AD converter. Okay, and this is the diagram, okay, which we can see here for that, where analog input is given, voltage comparator. This is the OR, okay? If you want, you can write this much. Okay, guys. So if you want, you can even write this much part as we can, as you as it is visible here, or instead of this, you can even write this much part. Okay, both are same mostly. Now, the last question, question number 5. So here we can see we have to convert the binary number into gray code, then the XS3 code. So let us do this. Here we have got some number of binary. We'll write the binary number here first. Okay, so this is a binary number. We are converting it into grayscale. The number before that will exactly be present as usual, no changes. Okay, so 1 1 0 0 1 1. What are we doing here? So 1 0, it is passing here. Okay, 1 plus 1, which gives 0. 1 is again carryover. So we have wrote 0, 1 is carryover. So 1 plus 0 is 1. We have wrote 1. Then again, we are taking it here. It will be again same 0. So this is how the grayscale has been presented here with the help of binary, which is again converted. Okay. After that, the step 1 is to binary to decimal part, where we are dividing, sorry, where we have got this binary, we are converting it into decimal, where 2 raised to part is being shown, as we can see here. Correct? From 2 raised to 3 to all of them. The important part is being shown only. And the answer refers 205 to the base 10. Okay. Now after this, we have got the decimal part. We'll convert again into BCD, where we are dividing it specially of 4 4. Means like we are getting 205 here as an answer. Okay, so we have root 2, 0, and 5. 4 different digits of that particular binary. Sorry, of that particular decimal, but converting it into binary of 4 digits or 4 bits. We exactly see that. After doing that, we are going to add this. Add with 3. 3 means with every side, okay? 3 ka binary, which we say especially. I think so this is clear. And then after that, we'll get the excess report. This was only for 4 marks, guys. This much. No, no, it is not for 4 marks. This was only the one question which is here, and both of those two questions. So all of those 3 questions are for 6 marks. Okay. After that, we have to perform the BCD addition. Where what we have did, we have written the binary code of 17 and 57 here, which we are adding. After adding this, we can see the valid and invalid part. Okay, it is approx for half marks. Then we have to add this number to invalid BCD. Okay, by adding this, what we can see, we have got some of the output. Basic addition, nothing else. So after this, we have got the answer 7 and 4. Okay, now most of you will be like, on what basis you are giving this? 7 and 4 parts. So we have divided all of them into 4, 4. Okay, I think so this is clear to everyone. What are we exactly doing here? After this, now we'll do the binary addition. BCD addition and binary addition are two different. So here we have got some numbers with points and now we are adding them. So before that, we have wrote the numbers, okay? Then we have added a subtraction sign and we have subtracted it. After doing the subtraction, okay, what are we doing here? we are writing this part here and adding it with this part. Okay, I think so this is clear to everyone. What are we doing? After doing minus, we got this, and then we did the addition part. Okay, guys. After this, we'll now move further. Design a 4-bit triple counter using JK flip-flop with a write truth table and waveform. So I think so this we have done before, yeah guys. But yeah, then to will write it again. So this is clock. It is also known as CLK. Okay. Here is the reset part. After reset, this is the logic one everywhere. Okay, logic one. It's QA, QB, and QC, QD. After that, this is JK, Q dash C, and yeah, so on. So now as we can see how things are here, it is all binary of 0 to 15. Okay, binary of 0 to 15. Okay, from QD, QC, QB, and then QA. Okay, after that we are writing here the waveform where we are using this part. I think so this is clear to everyone. Yeah, guys, same from this side. Even we are adding a layer of particular part, which is again an enhancing and rich look here. After this, we can see a basic clock has been given of 0 to 16 because numbers are here from like 0 to 16 of kind of. Like, sorry, 0 to 15, which is again counted as 16. After that, we are showing here LSB and MSB and all those numbers, the combinations which will be there. Okay. After that, we'll move to the next part, which is calculate the analog output of 4-bit with registered type DAC for inputs. So here we have got two questions. Assume VFS holds a range of voltage of 5 volts. Now we have assumed VR equals to VFS, which is again 5 volts. Okay, here 5 volts, which is again given us here. We can see this. Correct? Now the formula used is this one. Now here we have to learn some of the basic formulas where we can see the V0, like or VO is equals to minus VR bracket V1.2 raised to minus 1. Plus same for 4 as well, till 4, okay? After this, we'll substitute the values properly here in the formula. And after substituting and using the calculator FX part, like FX plus something ES 82 ES something. Okay, so this is the answer, but it is in what watts? Because this is the unit which is important again. Okay, after this, we have again got something. So we will be writing here and implementing it using the formula. Okay. Now question number 6. Attempt any two of the following, where we have to compare all of those TTL, CMOS, and ECL. Okay. So as we can see here, this is only for 6 marks. Yeah, if we write it properly, what it is exactly TTL, which says basic gates. So it is having NAND, CMOS is having NOR and NAND, and ECL is having OR and NOR. I think so. This is clear to everyone. After that, there will be propagation delay. The propagation delay is always having 10. Here it is 70 by 105, and here it is 2. But fan out time is again 10, 50, 25. Same. Power dissipation is like 10 meter watts. It will be like 1.01 meter watts here in CMOS. And here it will be like 40 to 55 in ECL. Then like noise immunity is like 0.2 watt. But here if we see as comparison with those two of them, so it is having 5 watt and 0.25 watts. This is again far better. Okay. After that, what is a speed power project? Sorry, speed power product. So it is having 100 TTL. In CMOS, it is having 0.7. And in ECL, it is about 100. Okay. As we can see some same pair values here. Now let me just do something for them. This 10, 10, again 10, and again this part. Okay. So this will be better in terms of understanding the part. Now we'll move to the next question. Question number B and question number C. So yeah, guys, only two questions are remaining now. So we'll end the live after two of those questions. So design a BCD adder using IC7483. Okay, where what we have to do, we have to label the combinational circuit, which will be drawn using universal gates as well. Okay, it depends on us what we are using. So to implement BCD addition, we require 4-bit binary adder for initial addition. Then the logic circuit will detect sum greater than 9 and one more 4-bit adder to add all those digits in the sum. If sum is greater than 9 or carry is 1, logic circuit to detect. So here what it is exactly happening? It is telling the basic rules which will be followed. Okay. Now the logic circuit is to detect sum greater than 9 can be determined by simplifying the Boolean expression with a truth table. See, I know this truth table, everyone knows this truth table. They are all binary numbers, if I tell you truly. Okay? So the binary numbers are from 0 to 15 for now, I think so, correct? And here only this much are present. Okay, present means this present. 1, 1, 1, 1, 1, again 1, 1, 1. I think so this is clear to everyone how things are being shown there. Now, this is the basic what is happening in our code. Yeah, if you see properly, it is like y is equals to 1 indicates the sum is greater than 9. We can put one more term, which is c underscore out in the above expression to check whether the carry is 1 or not. If we consider 1, it is satisfied. We add 6, 0, 1, 1, 0 in the sum. With this design information, we can draw the block diagram of BCD adder as given below. So this is the basic diagram of that full add especially. After this, today's our last question, which is again, design a 3-bit synchronous counter with or using JK flip-flop. Okay, so JK flip-flop. So our first step is like construct JK state table with correspondence excitation table, where the output state transitions transitions. Okay. Then there is present state and next state. Present state includes Q2, Q1, and Q0, but next stage includes same. Okay. After that, here we can see what it is exactly. All those are binary if you see properly. Okay. All those 1 1 1 0 0. Yeah. Then this is the basic like flip flop inputs. I think so. This is clear to everyone. State table and correspondence excitation table. D equals to don't care. Don't care. So here we can see the key map. Now only I mentioned the thing which is present, it is giving 1 and others are giving 0 or the cut sign. Now after that, this is a diagram where we have to represent the complete design of the JK flip-flop. So now here what are we exactly using? So we have give some basic names CLK which is again clock. Okay, CLOCK clock. Now after this, we can see here FF0, FF1, again FF2 and FF2 across. Here it is our edge triggered, which we can see apart. Okay, this is our basic Q0, Q1, which is giving the output in the form of this Q2. Okay, and yeah, today's lecture has been over here, guys. If anyone is having any doubt, they can comment below. Okay, now we'll have the lecture of DTE again tomorrow. Bye, guys. Have a good day.